Okay, so let's start a brand new project. And I'm going to just do this with a main program, just because it's probably a little bit simpler. I'm going to do it with the smallest example I can. So we'll include a main. And we need some test data here. Normally I would make a class to do this, but I'm feeling a little bit lazy, so I'm just going to make a simple integer array of things. So here's a bunch of numbers which are going to play the role of students or whatever we're going to do. Okay, so the trick is I want to use, instead of doing a for loop to go through and do all of these numbers, I want to write the recursive version instead. Okay, so suppose this is the teacher example, and that's the column of students who are sitting at the desks. How do I start this process going? Playing the role of teacher here. So give it to the first person, and I'm gonna say print array and do something with that pile of papers. Okay, so that's the teacher saying to the first student, do some work. Okay, so let's talk about what we say to the student. The thing that we're passing it is an integer array of numbers. Just out of interest's sake, which one should they start with? Move this down here. Way back up here, what's the first one that they should do? Why not start with the first one, which is the 0 position? I'm just going to be explicit. I want you to, here's this list of things, just start out at the 0 one. Okay, so here's the numbers, and here's the position that I want you to say. So, hand this pile of papers over to the student, and I say, tell me what the word is on paper number 0. So that sounds like a print statement. So we'll print numbers sub R1. Oops, sorry, in general that's numbers at whatever position it happens to be. So there's the first student. They've said 5. What do they do next? They take the same instructions that they had with the pile of papers, and they turn around and they say, oh, instead of saying the one I already said, I want you to say the next one. So if I said 0, I want you to say everything starting from 1. So this is Tom Sawyer. I painted fence board number 0. Now I'm going to turn to somebody else and I'm going to say, hey, I want you to take all of the rest of the boards starting with number 1, and I want you to do the same thing I did, which was just go and say whatever's on the board. Think it'll work? No. Well, let's just give it a try and see what it does. just out of interest's sake, we'll just run it. Oh, it did some stuff. It printed all of the numbers. It just didn't stop because there was no reason for it to stop. Okay? But certainly it printed all the numbers. And then it ran off the end of the array, which was position 5, because the array only has positions 0 through 4 in it. So it hit the number 5 position and it died. Notice anything interesting happening down here in the stack trace?
It just kept going.
It's all print array all the time. So it's the same thing over and over again. It's the same function being called. What's the difference between them?
Position.
Just the position is the only thing that's different. Well, okay, well that seems sort of interesting. Let's just go look at this in the debugger. Much as I said, the debugger is not going to help very much. We'll just go have a look and see what the debugger does with this. So we call print array with 0, and I'm just going to do a bunch of step overs just to let some things happen here. Oops, that was one too many step overs in the wrong place. Let's try that again. Now I'll go back to this code, and instead of printing the breakpoint there, I'm just going to move it inside there. And now I'm going to do a bunch of step overs just so that I can get sort of halfway through. There it is, printing the numbers. What's happening with our stack? It goes one deeper each time. The last level says, this one says 3 that we're currently on. If you click and look here, there's the person saying the 2. Why is that one still there? Because they're waiting for the number 3 person to finish their part before they eventually come back. Okay? And so what's going to happen here is there's going to be somebody waiting for as many boards of the fence as there are to paint. Everybody's just lined up, and it's not until the last person paints their last board and says, oh, I'm done, and they go work their way backwards, that everybody goes done and starts to leave. But they're all doing the same task, just at different board numbers. Okay? So this is why I say it gets sort of confusing when you go to look in recursion, because you'll see this whole whack of names that are all the same because they're just doing the same thing at a different place. And they all have to go reach the end before they're done. So if we've got 1,000 things on this list, we're going to have 1,000 print forwards showing up in our stack until we hit the last one, and then it should start to come back, except this one doesn't come back. So how do you make it come back? So we have to have some check here to make sure that we haven't run off the end. Where are we used to putting our checks for special cases? Right at the beginning. So a special case here could be something like there are no boards to paint. There's nothing on the list. How would you know if there was nothing to do? If the position that you're supposed to paint is what? Bigger than the number of boards that you have, which is numbers dot length, then you know that there's nothing left to do, and so you would get out. So even if they hand you, if they say, here's your numbers array, start at position 0 and it's got nothing in it, ha ha ha, well that's the easy case. If there's nothing in it, position is greater than the number of things that I have on the list, I'm just done. Or the general case is, as soon as we run off the end, whatever end happens to be, we're just done.
In that case, wouldn't the very last guy never record his position or whatever?
He never says, he never has anything to say.
Right.
He's the lucky guy. He's standing past the end of the fence, and somebody comes along and says, here's the stuff you're supposed to paint, and here's your instructions. And he looks and he goes, oh, nothing to paint here, done. Perfect. Okay? So the last guy doesn't ever say anything because he's already past the end of the fence in Tom Sawyer terminology. So if there's no fence to paint, don't bother. However big the fence is, if somebody hands it to you and says nothing to do. Okay? So this completed code, I guess we should run it and see whether or not it works. Greater than or equal, if we're lucky. So equal to 0, position 0, greater than or equal to 0, it needs to stop. There we go. Okay, and now it stops like it's supposed to. Okay, this little example has all of the elements of everything that's important in recursion. The first thing that's important in recursion is that there's always somebody who starts the process off someplace. Okay, so in our teacher passing papers analogy, this is the teacher walking up, not a student, as the controlling person and saying, here, let's get this ball rolling. Right? Let me go and speak directly to the first student and ask them to do something. Okay? After that, what you've got is a set of instructions that's common to everybody thereafter of what they're supposed to do. And they do their work, whatever it happens to be, in this case just saying their name or saying a number at that position. And then they make the problem smaller by removing one of the things, one less board to paint, one less piece of paper that gets passed on. The problem becomes smaller, but you take the same stuff minus the little bit, pass it on, and say, do the same thing I just did. Okay? And so there's that key that whatever I just did is the same thing that you have to do with your stuff. And someplace this thing eventually has to stop. And so after you've figured out what the normal thing is, you always go back and say, what's the ha-ha thing where I wouldn't have to do anything? Oh, if they gave me nothing to do, I would be done. And nothing to do means we've run off the number of boards to paint. There were either none to begin with, or we've gone through all of them and I don't have to do anything. Okay? And so that's the special case there that says here's a reason for stopping. In recursive terms, this is called the stopping condition, because that's what it does. If you don't stop, it just keeps going through. Okay? So notice this follows almost exactly our logic about how I've been getting you to write if statements for special cases. It's always very first thing, think of a special case, a reason why I wouldn't have to do anything, done. Okay? That still works just fine for recursion. Okay? Questions about that? Seems fairly straightforward. Let me play one little game with it. What did that do?
Didn't go backwards then?
So what's going to happen to this order?
It's gonna go 87.
It's going to go in reverse order. So this is, instead of printing the array forwards, actually does print backwards. Goes from the other direction. Because everybody keeps waiting and waiting and waiting. Can't say your name yet. Got to just take my paper and pass it on. Eventually the tapping comes from the back of the room, and then everybody gets to say their name from the back of the room forwards. Okay, so these two lines can be interchanged, and it just interchanges the order that you start with. But that's about all that it does to this equation. It's still the same basic idea. Here's a reason, here's the thing that gets things started. Here's what we have to do for work. Here's what the next person in line has to do for work, something smaller than what I did because we're now one position farther in the array, and then some reason at the top for stopping.
That seems easier than the original.
Now we get to the question of, it seems easier, which one should I use? What's the problem with this one in terms of stack space?
Eats it up real fast.
Yeah, you eat up stack space really, really fast. And notice that there's actually two reasons for eating up stack space. You eat up stack space because every time you call a subroutine or a method in Java, you're now got one extra thing on the stack. The other thing that eats up stack space is the number of parameters that you have across the line. Because you've seen from assembly language that every parameter also gets put on the same stack. And so the more parameters you run off the line, the more stuff you pass down to each level to get it to do the work, the more likely it is you're going to run out of stack space. So recursive stuff by nature takes more stack space than regular stuff does. So now we have the question of which one of these should you normally write?
Half more.
Recursion for smaller, situation. Whatever's gonna be easier to read.
This is sort of the whatever is easiest rule, but whatever is easiest normally is whatever you've already been taught to do, which is the iterative thing. So in Java and most programming languages, the iterative is typically the name of the game. So as a first go, probably 99% of the stuff that you write, you're gonna do in the iterative way, just because that's the normal way that people are used to seeing it. So writing this example this way doesn't buy you anything, because it's easier for people to understand with a loop, a counted loop or a for each loop, and it takes a lot less stack space to go through and do it than to do it the recursive way. So why bother with recursive? Obviously, this example isn't
Bragging
great.
rights?
Huh?
Bragging rights?
There are some programming languages where it's all recursive. Sure, fine. Then your choice is will you write it recursive because that's the way that people are used to seeing it. It's just 99% way if you want to do recursive stuff. So we still haven't found a reason for it. So here's the fight for reason for doing it. You're trying to write this thing iteratively, and every time you try to write the thing iteratively, it just doesn't seem to work. And you're sort of stuck. And so then you go, oh, what if I wrote it recursively? Let me just see. Go to try it recursively, and you go, oh, this just makes sense. It's easy. Okay? So the usual reason for writing something recursively is that you tried the iterative thing and it just doesn't, you're squeezing and trying and nothing seems to work, doesn't fit the problem. You look at the iterative solution, it's just like, oh, shrug, that's obvious. 3 lines, why wouldn't I do it that way? Okay? So we're gonna discover that there's some problems where doing things the recursive way actually works better and is more obvious to think about. And guess what? They're usually the more complicated problems rather than the simple problems. Okay? So let's try another sample, and we'll probably write the code for this next week at the rate we're going. Let's see. It's Friday night, you've been to the gym, you want to impress your friends, and so you decide that you're going to do some feat of strength. Back in the, I guess, 1940s and 1950s, the thing to do as a party trick was to show people that you were so strong that you could rip the phone book in half. You remember those phone book things? They used to be about this thick, and people used to look, you might not, I'm not sure if you've seen one.
It's actually quite easy.
Okay. Okay. So we decided the trick, by the way, to ripping the phone book in half if you want to do it at a party is you bake the phone book first so it gets really brittle and then it's easier to rip.
I think there's also some sort of way you can do that where you fold it in half while you're actually ripping it.
Okay.
Yeah, they did.
But let's go back. Let's think about the reason that we're instead of ripping the phone book in half. Let's suppose that what we're trying to do is we're trying to see if we can find somebody in the phone book back in the days when that's how you had to look them up. This example is going to go away really quickly in the next 3 years when nobody knows what a phone book is. But okay, so we're searching for somebody in a phone book. What do you do to find somebody in a phone book?
Open it up, see if your letter's earlier or after where you're at.
Okay, so you open it up more or less arbitrarily. When
wanna look up their last.
Got the phone book open. Now what do you do?
Wanna check their last name down there.
See where you are.
See where you are in the book. That's where the ripping comes in. So they're either in this side of the phone book or in that side of the phone book.
So they have to know.
So
See, Sarah, you put to the side.
now's the time where you rip the phone book in half. What do you do with the part that you know doesn't have their name?
Toss it out, eat it.
Toss it out. Okay? What did that tossing out just do to the amount of things that you have to search? It reduced it by half, which is
Well,
pretty much the best that you can do, right? If you're really good, rip it by half, throw the half away. Got it. Now we've got this, you know that they're in this half of the phone book. Getting a little lazy, getting a little tired.
Repeat step.
What's a good thing to do?
Just open it somewhere.
I'm too lazy.
Do the same thing you did.
Eat it.
Blow on
Give
it.
it to the next guy.
Here. Here's a phone book. I'm looking for so-and-so. Please find them for me. So what have I given them? I've given them the phone book and the thing I'm looking for. And I've said, here's a smaller version of the problem. Now not just by one, but by half of the phone book. Here's the smaller version of the problem. You go find it. I'll wait. What do they do?
The exact same thing.
Same process all over again. Doesn't matter what's in the phone book, they can see that it goes from S through Z or whatever, and you're looking for Thompson or something. They play the same game. They just arbitrarily rip the phone book in half, and they go, guess it's not on this side. It must be on this side. What do I do with this side? Oh, look, there's one of my friends. Let's just get them to do the work. Here's the person I'm looking for. There's the recursive solution. It's not me ripping the phone book. I made the problem smaller. I handed the same problem off to somebody else with a smaller version of the problem. I'll wait.
How many phone books have you gone through in your life?
Lots.
Is that how
Okay.
you look for phone numbers all the time?
Yeah. It used to be something you had to do.
Yeah.
Okay, so now let's ask the question about efficiency. In the case of me, let me do it the silly way. The way that we've been searching for things so far with index of is to do what?
Start at the beginning.
Start at the beginning and go to the end until you find the thing or don't find the thing, right? If you, for kids who know how to use the phone book, when they're like, what, 6 years old, or I guess 8 or 10 when they know what the alphabet is and they know the order things go in, how do little kids search? The kids that know the phone book, how do they search through it? They don't do the, let me start at the beginning, oh, there's A. Alfredson, oh, let me, is that it, is that it, is that it? They're already smart enough, what solution do they use? They use the alphabet.
Just the last name.
They learn the recursive solution. The recursive solution is open up the phone book to an arbitrary place. Oh, that's not it. It's either here or there. Oh, let me take this side. Let me split it. Oh, take another guess. Oh, it's there, right? So you got kids in grade 3 or whatever it is after they've learned the alphabet that they know the recursive solution to finding stuff in the phone book, more or less, right? They just don't pass it on to their friends, but if they were lazy, they would figure that out too. Okay, so back to the question about what's the easier solution. The easier solution is not to go, and the easier, more efficient solution is not to go through front to back, but to just do more or less the recursive thing and, oh, okay, this is where it is. And the fact that we're throwing away stuff along the way, half of the thing, gives us just about the most efficient search possible. Okay, so now here's the trick question. Suppose that we've got a phone book that's 1 million in size. How many friends do I need to find somebody in the phone book? Any old person. Million people in a phone book. So pretty hefty phone book.
Same amount as a smaller person.
How, if I had 1 million people in the phone book, if I do the linear search, which worst case? Million. Find Z. Ziggertson someplace near the end. Oh, okay, there they are. Been all the way through 1 million entries. Okay, so a lot of entries. Okay. How many rippings do I have to do for 1 million people maximum? It's a good party trick. Here's the New York phone book.
6.
Give me any name. How many rippings is it gonna take? It's a very specific number.
More than 2.
So if you rip 1 million in half once, you've now got 500,000, you've got 250,000. So they're decreasing by basically powers of 2. So log 2 of 1 million is about 20. Sounds impossibly low. 2 to the 20th is about 1 million, right? Do it the other way around. 2 to the 20th, if you get your calculators out, is roughly 1 million. Really? You're telling me that in 20 rippings of 1 million entries, I'm guaranteed to always locate the thing? And it's actually going to be less than 20? That's worst case is 20 compared to worst case 1 million. Is this it? Is this it? Is this it? I've got it down to 20. Is this it? Is this it? Is this it? Okay. So it's just the power of 2. So 2 to the 20th is about 1 million, give or take, because the 19th to the 20th, someplace in there is about 1 million entries. So all of a sudden you got this incredibly efficient way of searching for things. Okay? And so what we're gonna do is we're gonna, next time around when we're doing the recursive thing, we're gonna do a recursive search, which is really the phone book search, in order to see whether or not we can locate somebody in the phone book. And so we're gonna write the code for what kids in grade 3 know how to do. And with that, we're out of here. Or I'm out of here.
Coming to the downside,